Okay, so thanks for coming to the community call for May. We've got an exciting one this month. We're lucky to be joined by Evan from NVIDIA, who's going to talk about the container device interface, which is a new standard that we've mentioned a few times on this call for making GPUs and other devices available in containers. So Evan is going to give some background and detail about that, and we'll have the opportunity to ask questions about how it applies to HPC and so on. After that, we've got a quick demo just to show GPU support in SingularityCE in the new OCI mode implemented via CDI. So we'll see that working. And then we'll get to the usual release recap for the recent 3.11.2 release and other development stuff. So I think without further ado, I'll hand over to Evan so he can tell us all about CDI.
Hi, yeah, thanks, David. Yeah, thanks for having me on. I think just let me find my slides here. I did prepare some very boring looking slides. But just find the window on the side. Okay, can everyone see that? And let me enter the slideshow mode there. So yeah, as David mentioned, I'm Ivan from NVIDIA, and I should really sort of call out some of the other people involved in the CDI initiative. And that's Alexander Kanevsky from Intel, Christian Litke from Intel, and Ed Bartosz from Intel are very active, as well as my colleague Kevin from NVIDIA as well. It's a open sort of, let's call it cross industry or partnership between Intel and NVIDIA that we've sort of been driving the standard forward. And today I'll just be trying to, I think, give a bit of an overview of what CDI is, why we think CDI is cool and important, and what's next. And in all of these, I'll obviously be coming at it maybe a bit more from a let's call it cloud native and sort of cloud focused containerization point of view, but also trying to make the case why this standard may make sense in HPC applications. And at the end, I'll just sort of finish off with what's next, maybe just give a bit of an outlook from in terms of what we as NVIDIA and I think the CDI, the working group that's driving CDI are looking towards. If there are any questions, please let me know. I don't know if I can see people like raising hands or something like that. So maybe just give a shout, maybe not all at once, or we can keep them all to the end and then I can try and follow up after that. Okay. So CDI, as we say, I think acronyms are great, but for people who haven't heard of it before, it's the Container Device Interface. And it's a CNCF sponsored initiative that sort of aims to standardize the way that complex devices are exposed to containers. So devices have for quite a while now not just been single device nodes on a node. And in order to actually use a device, capital D device, like an NVIDIA GPU or some Intel FPGA, you need more than just that single device node. You need some drivers, possibly some other sort of IPC sockets mounted in. You might need to perform some initialization on the device. So there's sort of a bit of setup that's required before a user has access to the device. On a node that's running there, like bare metal, that's probably been done at boot by some script that was installed by an administrator. But in the cloud native sort of containerized world, you want to be able to do that same thing in a containerized environment. And I think some of that translates to HPC as well. And so CDI basically just defines this, what a device or resource looks like. So when I say device in the CDI context, I actually mean capital D device, and that is like a resource, a GPU, a FPGA, something like that, and not the specific device node that may be associated with that. And what CDI does is it allows vendors such as NVIDIA or Intel to describe these resources, these devices, in terms of modifications that need to be made to a containerized environment. It's very container focused because that's where it originated, but you can see this as a set of device nodes, file system mounts, environment variable, and hooks that hook into the container lifecycle, pre-start hooks, pre-create hooks, post-start hooks that need to be run in order to have a device usable and accessible in a container. And the whole idea is that vendors, as I said, are responsible for writing these specs, defining these specs, so that their devices, their resources are defined in terms of these modifications, and runtimes that understand the spec, are consumers of the spec, can then read those specs, make the modifications, and make the devices accessible to the users. So I keep skipping ahead on my slides. Maybe it's because I either don't know what I'm talking about or I do. Anyway, so yes, CDI-enabled container runtimes in the cloud native sense, then read these specs, make the modifications, inject the device nodes, perform the mount operations that are required for the driver libraries that exist on the host, for example, execute the hooks at the particular points in the container lifecycle so that those devices are then available, those resources are available. And we already have a sort of growing list of container runtimes, OCI, sort of OCI focused container runtimes that support CDI. As David mentioned, we'll be demoing the support in Singularity in the OCI mode. It is in progress. There are still some rough edges, but I believe, David can correct me, is that the target is to get this into the 4.0 release, at least as an experimental feature. Podman has CDI support enabled by default as of Podman 4.1. There are some caveats in terms of which specs are usable, but the support is there. Cryo also has CDI support on by default in Cryo 124, I believe, 125 and 126. And Containerd just released CDI support in 1.7. It does require a feature flag to be enabled, but it is included out of the box. And specifically, Cryo and Containerd are important for us from a Kubernetes perspective, since these are the runtimes that are used in Kubernetes installations. So we're building better support for devices in Kubernetes using something called dynamic resource allocation, and the Cryo and Containerd support for CDI are central to that. Docker, both from a CLI and from the daemon perspective. I see Maximilian has a question. Just let me finish up on Docker, and then I'll reach out on that. Docker, the support is in progress. We have PRs out against the daemon and against the CLI to add the support for CDI. I've got some examples of how like the interaction looks from a CLI perspective later, and I think David will show that as well. David, I believe Maximilian wants to know, is CE also included in terms of the Singularity support, or will you cover that in your section later?
To answer quickly, so this is being developed in the SingularityCE main branch, so the development branch of CE, it's there. And it will be in the 4.0 release of CE, and it will roll down to Singularity Pro as well when that comes out.
Okay, cool, thanks. Yeah, we can follow up on that later, I think, but I think that should answer that for now. Cool. So maybe give you a quick example. So from an NVIDIA perspective, since that's what I tend to work on on a day-to-day basis, we have a CDI spec, an example of a CDI spec here on the left-hand side, and a spec contains a number of devices. Each of them has a name. I'll get to the names later. And you sort of define these container edits, which I said was the edits to the OCI container, or the environment that you're trying to set up, consisting of device nodes, mounts, and these hooks that hook into the container lifecycle. In this case, for example, this hook is executed at the create container phase, which is well defined in terms of the OCI runtime spec. And what this hook will do is update the LD cache so that these libraries that you're mounting into the containers environment are actually visible in the LD cache, and you don't need to do any strange LD config magic behind the scenes to get this working. In theory. Oh, sorry, now I've gone and messed my pencil up. Okay, let's go back to mouse. Can I clear those? Clearing all drawings. Okay, so the spec on the left, you'll see that there's this vendor. There's a concept of a vendor, in this case, the NVIDIA.com part and a device class. GPU in our case. And together those define a device kind that a spec file refers to. And a device has a name, in this case 0. It's common for people using NVIDIA devices to access devices by index. And in this case, we use the index as the name. You can use the UUID as the name, or you can give it any other arbitrary name. There are some restrictions in terms of valid characters, but just think of this think of the combination of vendor, class, and name as a unique identifier for a particular resource, right? And we refer to that as the fully qualified device name. So we may also, as NVIDIA also has networking devices, etc. So maybe a device name could be nvidia.com/networking equals, and then some device name associated with that, so that those kinds of resources can also be accessible in a container. Other vendors may have different naming schemes, but as long as you sort of have this vendor class combination in addition to a locally unique device name, then you're able to uniquely identify a device associated with a particular vendor as well. And the idea is that referencing this fully qualified CDI device name when you're requesting your resources will cause all of the edits defined in the spec to be applied to this environment associated with this container. So in this case, it will inject the device nodes NVIDIA 0 associated with GPU 0, the control device node that may be associated with that, as well as a set of host level libraries and hooks that are required to actually get things working. And I don't know how familiar you are with the current sort of NVIDIA container stack, but currently what happens is there's a pre-start hook that does all of this stuff behind the scenes. I think that's the -NV flag, or one of the NV CLI, I think, flag on Singularity. What that does is it actually modifies the container's environment behind the scenes as a hook that's, well, maybe not in Singularity, but in other containerized environments. And that's sort of not, so that modification happens behind the scenes. A runtime such as Containerd or Docker or Podman is not aware of those modifications. And that does cause to sort of like subtle bugs. And for example, handling cgroup v2, which is become more common these days, is tricky because we actually have to build support for cgroup v2 into that hook that we run in the background. Cool. I'm gonna skip to the next slide. Now, maybe let's get to the why. So I've given a quick, very quick overview of what this is, and why we think CDI is sort of a good way to go forward from where we are now. And basically it allows vendors to have control over what a device, capital D device, a resource, means to them. So from an NVIDIA perspective, we know what the system level interfaces are to have access to our devices, what libraries associated with the driver, tools are required to give users meaningful access to that device. So we can, using the spec, write that down, and we don't need to integrate with specific engines, right? So the CRI-O support, the Containerd support was contributed by members from Intel, but working with the Containerd and CRI-O community. The Singularity support that David will be demoing later was implemented by the Singularity. That means that we as a vendor, NVIDIA, did not need to go and build support into each of those different container engines. And as a bonus, it means that an Intel generated CDI spec also works in those situations, right? In those environments, without them having to do anything. And any other device vendor can then define their spec and automatically have that work in any of these environments where CDI is supported. That's the beauty of open standards and specifications, right? What's also, I'll show a quick block diagram later, but what this also gives us is a logical separation between CDI spec generation and spec consumption, right? With our existing sort of hook-based mechanism, there's this weird, the container life, or the decisions made about what to inject is made at runtime when the container is actually being created. Instead of us having the power to say, like, generate the specs once and allow us to name resources sort of offline and separate that from running and consuming those resources in different environments. So I think that is useful, I think, from our perspective as well. And because we're using an open standard, it allows like uniform UX across vendors and tools, which wasn't true, at least for NVIDIA devices up until now. I've used Engine here to be like Docker, Podman, Singularity, or any other CLI tool that understands CDI. And the idea is you say run -- device, give it the fully qualified device name and an image and the command you want to run in there, and it runs. I'll answer that question there, I think, Carlos. And the same is then for Intel devices. The same API is used there, okay? And from a daemon perspective, if you're talking over a web API or some gRPC API, you have the same thing. Some field that refers to a CDI device refers to this name, and it does not matter what vendor that is. It should, in theory, just work. I think Carlos asked if we can use MIG devices too, and yes. So this example shows GPU. We, as a vendor, can generate a spec that says what a MIG device is, right? What is required to access a MIG device. And for example, the tooling that we have can generate the specs for available MIG devices in the system. And the default is to index those or access those via index. So the device name would be nvidia.com/GPU equals GPU index : MIG device index, right? So 0:0 would be the 0th MIG device on the 0th GPU in that case. So does that answer your question, Carlos? So yeah, maybe in summary, any device that we can represent in the spec and give a name to can be used. So MIG devices are included in that. Okay, cool. Oh, where's my other slide? Oh, I skipped over it. Okay, so maybe this is a bit of a busy slide, but it just sort of summarizes what sort of CDI, how CDI works, and how it interacts with the different components in terms of the generation of the spec. Here on the, let me just see if I can get a pencil here again. There, draw. Okay, cool. So we as NVIDIA would generate the spec here and store it in some well-known location. So standardized locations /etc/CDI, for example, based on the state of the system at spec generation currently. And then once that's done, that's done. There's no need to regenerate those specs if the system configuration doesn't change, right? So as long as that system configuration, this can be done at boot, and those specs are then valid as long as that node is up, right? We do have use cases where we generate them dynamically, but from the consumer's perspective, that is also irrelevant in this case. Those specs exist in some location and consumers consume them from that location. So in terms of the OCI compliant consumers, which I include Singularity's OCI mode, it then consumes those specs. So a request comes in requesting a particular device. It reads the specifications, checks whether it's a valid device identifier. If it's a valid device identifier, uses the CDI package that we, as the in the Container Orchestrated Devices Working Group, have built to make the modifications to the OCI spec, and then forward that modified OCI spec to run C or crun, which then will invoke the hooks as defined and start the container process with access to the resources as required. Now, since this is the more HPC focused call, not all environments are OCI compliant. So for example, Singularity has this native mode, which does not use OCI as a mechanism of representing what needs to be run. Now, just a thought experiment, let's say, more than anything else at this stage, is our thinking is that there's nothing in the OCI, in the CDI spec, apart from possibly referencing container edits or devices or mounts, something that is like container focused nomenclature. But there's nothing there that says that those things need to operate on an OCI specification. In the end, it is a set of system level primitives, devices, mounts, executables that need to be executed at certain points in the life cycle. And our thinking, at least very naive possibly, is that those could be translated to serve non-OCI applications as well. The motivation being that vendors such as NVIDIA and Intel can still define what a resource is, and that can then be consumed by any CDI-enabled consumer, whether they be OCI compliant or non-OCI compliant. Now, obviously, the downside is for non-OCI compliant consumers, you can't use the CDI package to make the modifications to the OCI spec, because that's the only kind of spec we understand and are able to modify. But the same logic exists. This non-OCI, this consumer will look at the resources that or the entities that are required, the modifications that are required for access to a particular resource, ensure that those mounts are made available in whichever mechanism is used in that environment, ensure that the devices are made available in whichever mechanism is used in that environment, and execute the hooks to sort of set up the devices, etc., in whichever mechanism is used in that environment. So that's sort of the motivation from a CDI specification perspective. There is no direct or no strict requirement that any of this be OCI necessarily. Okay, no, I'm going backwards instead of forward. That's why I'm getting so confused. Okay. Okay. So what's next? I think where we are at the moment is we are trying to get more usage or more experience with CDI usage in general in this OCI space. The tooling to generate CDI specs from an NVIDIA perspective was released one or two releases ago for our NVIDIA Container Toolkit. We're still collecting feedback in terms of how useful that is. It is currently our suggested mechanism to use NVIDIA devices when running Podman, because especially when running rootless Podman. So one of the downsides of our existing mechanism for injecting devices is that it does really not work well with rootless environments. And it also, especially in environments where users need both rootful and rootless access to containers. So just because Podman supports it out the box, Podman is actually CDI is actually our recommended mechanism to use NVIDIA devices in Podman as of the 1.12 release of the NVIDIA Container Toolkit. We've also built CDI support into our GPU operator, which is used in Kubernetes, in the Kubernetes context, to ensure that containers are started with device access there. And we're collecting sort of information on usages, possible shortcomings in the spec, improving the user experience around generating the CDI specifications. You know, like we have tooling to generate the CDI specifications given the current state of the system, but like things can change, right? Drivers get installed or reinstalled, that changes the driver version, etc. Right? MIG reconfiguration happens. That means the spec needs to be regenerated, things like that. And we need to get to a point where, regardless of what happens from a device perspective, the spec that is generated is always the one that represents the current state, right? So I think there's still some improvements to be done there. And also, currently the spec is at, 0.5, 0.6 is in development. And although older specs are readable by clients that are implemented against a newer spec version, so we don't break compatibility in that direction, a client does error out if a spec is read of a higher version than what it supports. And there are some cases where that has come back to sort of like at least cause interesting user or non-ideal user experiences. We usually have workarounds in place, and we do, when we generate specs, try and generate a spec of the minimum version required. If you're not using advanced spec features, then we don't generate a version 6 spec by 0.6 or 0.5 spec by default. We generate a 0.3 spec, which is a version that is supported by most of the clients that I discussed previously. And as I said, we're here today to start this discussion about like, well, is CDI more generally applicable, for example, in the HPC space or the non-OCI use case in general? And then obviously, any additional feedback, questions, features, etc., would be welcomed. Sorry, I keep losing access here. Okay, cool. So I think just to close, if anyone has questions about CDI specifically and NVIDIA's use of CDI and access to devices in those kinds of environments, drop me an email. That's fine. I'll either mark it as spam or I'll respond. But no, I'm just kidding. I'll probably respond. Or the working group that is driving the CDI, the container device interface, is the Container Orchestrated Devices Working Group. You can create an issue there if you have questions about the spec itself, want to propose enhancements to the spec. You're welcome to do that. And David mentioned that there's a Singularity discussions. If there are CDI-related Singularity discussions, please tag me there and ask any questions. I'll try to get to those. We're also, all the CDI developers are active on the Tag Runtime Slack channel. If anyone has active access to that, obviously that's maybe a little bit more Kubernetes focused, but it's a good starting point to reach out and ask questions if anyone has any. So yeah, I do tend to talk a bit fast, so let me know if anyone has any questions or if I should clarify anything before. Thanks a lot for your attention.
Thanks very much. Do we have any questions for anyone? Anyone got their hand up or just want to shout out?
I guess I have a broad one, maybe. Just thinking, in HPC environments, usually you have kind of a job scheduler, right? Allocating resources above this. Have you thought much about how, a job scheduler might interact with this CDI work?
So I think that depends on the job scheduler. At the moment, the way I understand scheduling at the moment is giving access to a particular GPU, or at least from the NVIDIA context, right? Yes, there's sharing as well to be considered, but at the moment, the mechanism for giving access to GPUs is by setting, for example, CUDA visible devices or something, as far as I understand the scheduling mechanisms used in Slurm, for example. Now, I would see the use of CDI there as, instead of setting that environment variable, you would basically somehow, hand wavy somehow, reference a device that has been allocated for a particular job using its fully qualified CDI device name. So the plugins to the Slurm scheduler need to be extended to also understand CDI to determine which devices are available. Probably one can add metadata to them to understand what kind of properties they have, and then start referring to these devices using their device names instead of just indices. I'm not saying that we're quite there yet, but I think that's sort of possibly a direction to consider. Another thing on this topic is that, so I sort of briefly mentioned dynamic resource allocation in the Kubernetes space. Now, that is a change in how Kubernetes handles resources and actually allows resources such as the GPUs, more complex devices, to be managed by third parties or defined by third parties, actually. So from an NVIDIA perspective, we are writing a resource driver that fits into the DRA framework that allows us to give a richer API for user to request resources. So using this mechanism, instead of the integer counting mechanism that we have currently, you are able to say, well, I want a NVIDIA GPU with these properties, this model number or this model name, so much memory, and I want that to be partitioned into a MIG device of this size, and I want that to be shared using MPS with a sharing factor of 4, right? And this resource driver, not an NVIDIA GPU driver that talks to the kernel, is then responsible for allocating those resources on the node where this where the pod or container will end up being scheduled. And I think having that kind of flexibility and tying that maybe into these plugins with the schedulers that we're seeing in the HPC space might add more functionality than to just start thinking about these devices in terms of integer units, so that users would have a richer. If a user requests a GPU with 5 gigs of memory, you're able to say, oh, we have a device, we partition it, take a A100, which has, well, anything between 40 and 80 gigs of memory, but using MIG, it can be partitioned into up to 7 compute units with 5 gigs of memory, right? So allowing users more flexibility in that and exposing those kinds of richer APIs to the scheduler instead of relying on these integer sort of counting workarounds in the background, essentially. But yeah, that's something to explore, I think, going forward. I don't know if that answers your question.
Yeah, at least it gives me a lot to think about. Yeah, thanks a lot, and thanks for the
So
presentation.
I can drop the links for DRA, for example. We can start a sort of general discussion maybe on the Singularity discussions, and then I can drop some links there that give more resources. It's obviously Kubernetes focused, but I think there are some, and it's still in alpha, so we still have some work to do, and part of that is defining the spec. It also uses CDI in the background to actually request those resources. So just to summarize, DRA creates a spec dynamically once a request comes in and associates a unique device name with that set of resources that were requested, and passes that down all the way through down to the container runtime, CRI, or cryo, or containerd, which then performs the actual modification to the container's environment to give access to those devices. Okay, so yeah.
Great. Do we have any more questions?
Yeah, sure. Since you mentioned Slurm, I actually have a Slurm cluster that I manage at my company. We have some GPUs there that are frankly underutilized right now. I'm trying to get them onboarded and get some frameworks deployed. Do I understand right that so currently you're not aware of Slurm supporting CDI enabled containers?
No, I'm not aware of any. I know that, so my understanding is that GRES, right, is the plugin that gives access to or allows accounting on and gives access to GPU NVIDIA GPUs in Slurm. I don't know whether there has been any work to drive CDI adoption there, or CDI as a mechanism to define resources in that case. So yeah, a lot of what we've been doing has been focused on the, let's call it, cloud native applications. So where containerization is a little bit, well, I'm not going to say more well-defined, but at least has a specific spec in the OCI spec, and that allows us to reason more concretely about the modifications that need to be made. I think, so I'm not aware of any work. I don't know if anyone is doing anything. I think it's possibly would be interesting to explore whether it is useful, and then to see where that goes. I don't think that's like a short-term project, though. I think it's something that we should get started, and maybe in the longer term gives us benefits. Especially, I think from a vendor perspective, CDI is something that we see as the mechanism for defining what resources are going forward. And we'd like to extend that to other contexts outside of just Kubernetes and general sort of OCI compliant containerized environments.
Yeah, I guess I'm just thinking as I start deploying some of the frameworks and making these GPUs available to my users, if this is something I should be considering. It seems like maybe I should be holding off a little bit. This is kind of still looks like it's a bit future looking.
Yes, I think it's more future. If you want your GPUs deployed like tomorrow or in the next 3 months or 6 months, like I wouldn't wait for CDI support in Slurm. Timelines taken with a grain of salt there. I think it's more, it's an issue of prioritization and person power.
All right, good. Thanks.
Cool. Sure.
Anyone else? Okay.
Yeah.
Well, thank you very much for going through that. A lot of great detail there, and I'm sure everyone will have a good think about further questions to ask on GitHub by email or whatever. I know that you've got to present this in another call shortly, so please just don't feel you have to hang around. You can drop off once we get onto the non-CDI stuff for sure.
Cool. Yeah, I'd like to see your demo, and then I might just sneak out the back door, because yeah, I'm presenting sort of the same thing at the HPC Advisory Council meeting that follows this one. So maybe I'll see some of the rest of you there as well. Yeah, cool.
Great.
Thanks, David.
So I've dropped into a terminal here. I'm actually on an AWS instance, and this happens to be an instance which I think has a T4, a Tesla T4 GPU. So it's only a single one, and it's not very complicated, but we can have a look at how the OCI mode support for CDI works with Singularity here. I should mention that the work that's gone on behind this has been done by Omer, who's on the call, who joined Sylabs relatively recently and has really dived into some fairly complex stuff quickly. Let's clear this and have a look at the contents of my Etsy CDI directory, right? So I've got, in this case, a JSON file rather than a YAML, but here it is. This was generated using the NVIDIA CTK tool. And in this case, I got that just by installing the NVIDIA Container Toolkit base package straight out of the repo. This is a Red Hat 8 system, so it's got the CUDA repo set up on it, and the toolkit binaries and things were pulled out of that. And then using that, we've just generated a CDI config, and it's a little bit longer than the one that was shown in the slides, but you'll see we've got the devices here, and we've got the device, a single one called 0 in this case. And going down, we can see that we've got device nodes, we've got the hooks, which were mentioned, and container edits. And if you keep going down, you'll see a load of binds for libraries and things, which are going to end up in the container. So there's our config. Now, if I want to run a container, there we go, using this config, then it's just a case of in the --OCI mode, adding the device flag, and then putting that special format, which was mentioned in the slides. So I got the vendor, nvidia.com, the class is GPU, and 0 is the name of the GPU I'm going to use here. In this example, I've got something very boring, right? What I've actually done is I've got a Docker archive locally. So it's an OCI container, and it's just got one of the little CUDA samplers in. So I can run something very quickly and just demonstrate that what happens is the OCI mode is unpacking that container, and there we have it. We started a matrix multiply using CUDA, and it found our Turing GPU, and we got the expected performance out, right? So it's really simple, just a case of adding this device flag and specifying what you want to use inside the container. And then as long as the config is set up properly in the right place, then it should all fall out and things should just work. Now, one thing that Omer has added here that isn't shown on this example is that we actually have an extra flag that I could use here if my CDI config isn't in the kind of default location. So I could do CDI dirs and then I can specify directories to go and look at for CDI config. And this might be useful if you're kind of playing around with this and you're in a place where you're running rootless, you can't dump stuff into etc CDI. You can point it at different config files. So there we go. Very simple demo, but if you have GPUs and you would like to try it out, you can go and grab the main branch of SingularityCE, and if you compile it, this is now accessible to you, and you can start trying CDI out and give any feedback that you have. Any questions on this? All right.
Yeah, sorry. I think thanks, David. That's good. And yeah, Omer, thanks for doing that work. Yeah, as Dave sort of alluded to, these default folders are etc CDI, and there's also var run CDI, which is thought to be the location where, since var run is typically cleared on boot, that's sort of the location for ephemeral devices or ephemeral specs, right? Something that's generated dynamically, and the configuration is not expected to actually be there or be the same on reboot. But yeah, it's good to allow users to also generate or specify either a spec file specifically or a location for spec files to sort of pick things up. And yeah, the NVIDIA Container Toolkit since 1.12 allows for CDI spec generation. It doesn't always work as well as what it should. Like I said, the UX needs to be improved. But let us know if there are any problems. Thanks, David. Sorry for stealing the thunder.
And Omer has actually pointed out to me behind the scenes that I typed in the CDI DIRs in the middle of another flag. So apologies about that. It's a separate flag. Yeah, thanks again. And we'll move on now from CDI, and we'll get back to the kind of usual business of going through releases and the development updates. So I'll switch gears here, and let's jump across then to looking at the recent release we had of SingularityCE 3.11.2. Okay, so this one came out not very long ago at all, and you'll see from the new features and functionality section of the changelog, most of the kind of new stuff here is related to the OCI mode. So we've mentioned several times that in 3.11, the OCI mode is sort of considered experimental, and we're actively adding features into the stable release so that people can get experience of trying out the OCI mode before it becomes a more standard flow in Singularity 4, where we'll have the OCI encapsulation within CIF containers and so on that we talked about. But there's now support for setting host names, setting some of the kind of scratch directories and things like that, by mounting custom homes and so on that you can do with Singularity away from OCI mode. The 2 points down here, these bottom bullet points, are new additions to SingularityConf. So there's been, from the Aptainer project, there was a CVE published, which was basically around the fact that we in setuid mode mount file systems. We mount squashfs, or we can mount overlay extfs file systems, and we do that through kernel mounts. And in some older distributions, there may be some vulnerabilities in file systems which haven't been addressed. Now, this is the case for a specific one in extfs, where there's a denial of service vulnerability. And and it hasn't been fixed in Red Hat 7. It's been fixed in most other places, so 8 and 9 it's been patched, but it's there in Red Hat 7. Now, there's kind of differing opinions on the status of what the Apptainer project have put out as a vulnerability. We, on the Singularity side, on the Sylabs side, are looking at this from a point of view that the underlying vulnerability is in a file system driver in the kernel, and that's where it needs to be fixed. But there's a valid point for defense in depth if you're affected by this vulnerability and you don't mind losing some functionality to allow you to turn off the ability to mount the file system through the kernel. On the Sylabs site, we've got a blog post going into more depth about this and more reasoning. If you want to, after you've read that and kind of looked at the issues, disable users from using EXTFS file systems, then you can set this value in SingularityConf to yes, and then that will be stopped. There's actually an erratum which we had to issue for 3.11.2 that there's an error where the squashfs disabling isn't applying correctly to encrypted containers. We've got a separate option where you can disable encrypted containers, but this one should also disallow encrypted containers because underneath the encryption, there's a squashfs layer. If I scroll up here, we'll see that Omer is actually working on putting out a 3.11.3 release today, and that's going to have a fix for that option, okay? So that's what these are about, that ability to disallow these mounts if when you've kind of considered the background around this issue, had a look on the Sylabs site blog or read about it elsewhere, you can take action to kind of disallow these if you think it's relevant for your environment. Down to the bug fixes section, we have a change to packaging on SLES. I think I mentioned that one last week. We switched from requiring run C instead of C run because of differences between what's packaged in a community repository versus a more base repository. We have a fix for loop device creation, which avoids some issues on new kernels, and especially this was seen on Ubuntu in a recent update, where if the max loop parameter isn't set, then you can't create enough loop devices if you're running a lot of containers at once. So we've got a workaround for this issue in there now. And then a few kind of bug fixes around OCI mode, which are really trying to fix the behavior that wasn't quite right, didn't quite match with our target, which is running OCI containers natively, but with similar default semantics to Singularity's -- compat mode. So that's what's there. So that was out previously, and then, like I said, this 3.11.3 release, Omer is working on it now, and that will be out today, as long as I think GitHub recovers, because there's some kind of outage there. Any questions around the release? Okay. Outside of that, the development work we're doing is really kind of focused on the OCI mode. There's been the CDI work and continuing to go forward and bring more of the flags that are supported with a native runtime into OCI mode. So that will be continuing over the next sort of month. And I suspect that in the next call, when we give an update, it'll be more of the same, more features enabled in OCI mode. There's a question there. So Nathan asks, is there an expected time frame after a SingularityCE release when an RPM will be available in the Apple repo? Right, so we package Singularity for Apple, and Apple has a process where when you have a new release and you put a package in, it goes into an update system, and the update system, it'll be held there for a period of time, and it depends on whether there are votes on the package to give it karma. If 3 people give it the thumbs up and say it works, then it will go out into Apple. If people don't vote on it, it will take at least a week to get out in Apple. So yeah, the time frame for a release really depends on whether people who are have Fedora accounts actually go into the Bodhi update system and vote on those packages to say that the updates are good to go. Yeah, maybe actually I can probably, if I'm lucky, I can quickly take a look and share and show you. Because people might be interested in actually how to do this if they want to kind of test packages. So here we go. I'm at a Fedora update system, and Apple is kind of managed under Fedora's infrastructure. It's part of the Fedora project. And we can see that I submitted 3.11.2 updates 2 days ago, and for Apple 7, 8, and 9, they're in the testing state. For Fedora 38, they're in the testing state. But for the Fedora 39, which is kind of the development rawhide branch, they went straight to stable. If I click through to one of these packages, what we'll see is down here, it says it'll be stable by time in 7 days. So we've got 6 days left until these packages go to stable, unless it satisfies this requirement. So in order to kind of satisfy this, what we have to have is people with a Fedora account log into the system, and then they add feedback with a thumbs up. And if they add feedback with a thumbs down because they found it doesn't work, then it'll be blocked from going to stable. So that's how that works. Okay. I think oh, Omer is mentioning there as well. We do have, of course, RPMs out as part of each release on the GitHub page. So if you want to get something updated as quickly as possible, you can go and grab them directly from us. But obviously those aren't in a repo, so they won't apply updates automatically if you do that. Okay. Any other general questions or anything else people want to raise? We're getting to the top of the hour. It's been interesting call this time around, definitely. So please do kind of follow up on a Slack or on GitHub discussions or the mailing list if you have anything after the call too. Anything else? Okay, well, we'll say goodbye for now. Thanks for joining us, and hope to see you in June for the next call.
Thanks, everyone.
Thanks, DT. Thanks, everyone.